Einstein's equation from variational principle. Einstein equation can also be derived using the principle of least action in terms of a properly defined action. Now, from a single particle quantum mechanics, single particle classical mechanics, we see that the action corresponding to such a problem can be defined as the time integral of a Lagrangian, which involves the generalized coordinates qi and the corresponding generalized velocities qi dot t, and where the integral is taken from the initial time, say ta to tb. And at ta we will say that the initial point qi ta and qi tb are all fixed. Then the classical path is given by the one for which S is an extremum, which can be obtained by considering variation of qi about the classical path, and then we find the corresponding variation in the action. And if that variation is 0 up to first order, we would say that that particular path is the classical path of the particle involved. Now, such a problem leads to a differential equation in terms of this Lagrangian, and that differential equation is called the Euler-Lagrange equation. Similarly, in the case of gravity also, we can construct an action, and we can find use the principle of least action in terms of that action, and then obtain an equation which will be the Einstein equation. First of all, we note that the action involved should be a scalar quantity, so that the equations result, so that the action will be the same for all observers. Further, we also need to think about the dynamical variables here. We see that the Einstein equation is given by R mu nu minus half G mu nu R equal to minus K T mu nu, where T is the energy momentum tensor, R is the Ricci scalar, and R mu nu is the Ricci tensor. And this involves the metric tensor and its derivatives. So the dynamical variable over here is the metric tensor, and at every point in space-time, say given by x, which can be represented in terms of the coordinates x mu, x1, x2, x3 and x4, at every such point there will be a metric tensor which is a tensor of type 02. So instead of, say, discrete particles that we were discussing earlier, we now have the dynamical variables given by the components of metric tensor at every point in the space-time. So we have a tensor field over here, and an action for such a tensor field can be written as an integral over a region V of the space-time over the d4x, which is the volume element in the space-time. It's 4-dimensional, that's why I wrote it as d4x, times a Lagrangian density which involves G and its derivatives. Now we can find the set of values of the coordinates, the set of values of the dynamical variables for which S is an extremum, and we want the resulting equation to be the Einstein's equation. The requirement that the action integral is a scalar quantity, so that it is the same for all inertial frame, same for all frames of reference and all observers, puts some restrictions on the form of the Lagrangian and also of the integration measure over here that we can choose. First of all, we note that the space-time volume element d for x, which is dx1 times dx2 times dx3 times dx4, which I have written here as the product over mu of dx mu, is not invariant under coordinate transformation. So therefore, this is no longer an invariant quantity under the coordinate transformation. In fact, d for x bar, that is, if I consider a transformation from the set of coordinates x mu to the set of coordinates x bar mu, the space-time volume element will change from dx mu to say dx bar mu, and they are related by the following formula. So d for x would be given by the Jacobian determinant times, d for x bar is given by the Jacobian determinant j times d for x, where j is the determinant of the matrix given by say the j alpha beta is equal to dx bar alpha by dx beta. So we have a matrix with components j alpha beta corresponding to this transformation between the set of coordinates and x bar, and then j is the determinant of that matrix. So as we change from the coordinate system x to x bar, the volume element, the space-time volume element, transforms like this. That is, they are different. So d for x bar is different from d for x, and it is by a factor j. Now we also note that as we change from the coordinate system x to x bar, the metric tensor components, since it is a 0-2 type tensor, changes in the following way. G bar mu nu equal to dx alpha by dx bar mu, then dx beta by dx bar nu times g alpha beta. Further, we also have the following expression, that dx bar mu by dx alpha times dx alpha by dx bar nu equal to the Kronecker delta mu nu. This equation, and if I define say a as a mu alpha as dx bar alpha by dx bar mu by dx alpha, and say b alpha nu as dx alpha by dx bar nu, this expression can be written as a mu alpha times b alpha nu And if I write this, since it has two indices in the matrix form, I can write this as A mu alpha and this as B alpha nu. So this means this is equal to sum over alpha A mu alpha then B alpha nu is equal to, this is delta mu nu. So this is simply now the matrix product. So AB mu nu is equal to delta mu nu. or in other words, the product of the matrices A and B is the identity matrix. So now I can take the determinant of this. So determinant of AB is determinant of A times determinant of B. Determinant of identity is 1. Or in other words, determinant of B is equal to 1 by determinant of A. Now, the B is the matrix given by with components given by dx alpha by dx bar nu. So that is this matrix. So instead of writing this, I could also have written determinant of dx bar mu by dx alpha. So this means it is the matrix with components mu alpha given by dx bar mu by dx alpha. Similarly, this is the matrix with the alpha nu component given by dx alpha by dx bar nu. So the product of the determinants of those two matrices is equal to 1. So which means that the determinant of dx alpha by dx bar nu is simply 1 by j. The reason is this is the determinant of the Jacobian matrix, because we have defined the Jacobian matrix to be the one with the mu alpha element given by dx bar mu by dx alpha. So this is 1 by this determinant, which is nothing but j. Now again, similar to what we have done here, we can take the determinant of this equation. This is a matrix and this is a matrix and this is a matrix. So then we get the determinant of the left hand side is equal to the product of the determinants of this times this times this. Okay. So the determinant of g bar mu nu is given as or written as g bar. So that is equal to the determinant of this dx alpha. So determinant of dx alpha by dx bar mu times determinant of dx beta by dx bar nu times determinant of the metric tensor in the original coordinates. So that can be written as g. But from here we see that this is simply 1 by j and this is also 1 by j. So that means g bar is equal to 1 by j square times g. And that's exactly what I have written here. Or I can write j square as g by g bar or j as square root of g by g bar. Now g is a metric tensor in the space-time. And if we construct at a particular point the geodesic coordinate system, then we see that the metric tensor should reduce to that of the Minkowski spacetime, and which is given by eta, which is the diagonal matrix -1, -1, -1 and 1. So the determinant of the metric tensor in that coordinate system reduces to the determinant of eta, which is in fact the product of its diagonal elements, which is -1. So we see that the metric tensor has a determinant in this particular choice of the metric tensor that we are using, the particular choice of the interval that we are using, that it's given by a negative number. So this quantity can also be written as minus g by minus g bar. Now minus g is positive and minus g bar is also positive. So I can now separate this out into square root of minus g divided by square root of minus g bar. Since each of these quantities within the square roots are positive, and this is well defined. So that's what we have over here. Now we remember that d for x bar is equal to j into d4x. Now I can replace this j by this quantity. So that is equal to square root of minus g by square root of minus g bar times d4x. Now taking this to the left side, I have square root of minus g bar times d4x bar is equal to square root of minus g times d4x. So now instead of d4x, if I use this expression, that is square root of minus g times d4x, then we see that this is equal to the same object in the second coordinate system. So therefore this is an invariant quantity, minus square root of g d4x, and therefore while writing an invariant action, I should have the following form. So instead of d4x, I should have d4x times square root of minus g times a Lagrangian density. Now if I take the Lagrangian density to be a scalar quantity as well, this will be invariant under coordinate transformations, and as we have seen just now, this will also be invariant under coordinate transformation. So that action will be a scalar quantity which will not change under coordinate transformations. So we construct a scalar action over a space-time volume V with the integration measure given by this form, d to the power 4x square root of minus g, which is invariant, and we choose the Lagrangian density to be a scalar quantity as well. Now we have seen that the matter affects the space-time curvature. So T mu nu represents the energy momentum tensor, represents the matter, and that introduces changes in the curvature tensor, the Ricci tensor and Ricci scalar, or in other words, it changes the metric tensor. Now at any given point, we can choose what are called geodesic coordinate systems, a local coordinate system, in which the first derivatives of the metric tensor can be made equal to 0. We can make the Christoffel symbols to be equal to 0. Therefore, then we expect the Lagrangian density over here to involve second derivatives of the metric tensor. And we know that we have such a quantity, and that is the Ricci scalar R. So there are two things. L should be a scalar quantity, and the Lagrangian should involve the metric tensor and its derivatives, and there exists local coordinate system in which we can take its derivatives to be 0, and therefore we would expect the non-trivial Lagrangian density to contain terms which involve second derivatives of the metric tensor, and we are already aware of such a quantity, that is the Ricci scalar, and so that consists of the effect the matter produces on the curvature of the spacetime. Now the Lagrangian should also involve the effect of matter. So we separate the Lagrangian into two parts. The first one is called say SH. We call it the Hilbert action, and the second one involves the effect of the matter, and we call the matter part of the action. Now, as I discussed earlier, the Hilbert action involves, first of all, integral over the spacetime region with measure d4x times square root of minus g, and for the scalar Lagrangian part we take the Ricci scalar. And for the matter part, we again have the same integration measure, and we will have a scalar Lagrangian density which involves the effect of matter. So this should incorporate the energy momentum tensor, or this should be a scalar which is constructed from the energy momentum tensor. So now we have obtained the action, which is the sum of, say, the Hilbert action, which is SH plus SM, where SH is given by this and SM is given by this. We can now construct a variational equations. Now we will expect, so we will consider variation in the metric tensor field G mu nu x going to, say, G mu nu x plus delta G mu nu x, with this variation delta G mu nu becoming 0 at the boundary of the space-time region V concerned. So at the boundary of the volume, the space-time region V, we expect delta G to be 0. So under such variation, we consider the change the action undergoes, and we consider the set of values G mu nu, or we compute set of values G mu nu for which say delta S is equal to 0. So consider this variation, and where this variation vanishes at the boundary dV, and as a result the action changes from S to S plus ds, where this the variation delta S in the action can be written as the variation in the Hilbert action plus variation in S. Now SH is equal to integral over V of d4x square root of minus g times the Ricci scalar, and therefore delta SH would be the change or the variation in this whole thing. So the quantity that changes is the tensor field and therefore the Ricci scalar. So I can take this delta operation inside. So this will be equal to first the change in square root of minus g times r plus square root of minus g times delta of r. So we need to consider or compute these two terms separately. First, let us consider delta square root of minus g. So, so this is given by 1 by 2 square root of minus g times delta of minus g. But then, so this minus can be taken outside. So I have placed it here. So 1 by 2 square root of minus g. Then g is the determinant of the metric tensor, and therefore it is a function of the elements of the metric tensor, the components of the metric tensor. So I take the derivative of the determinant with respect to G mu nu first, and then multiply it with the variation in the components of the metric tensor. Now we have already seen that dg by dg mu nu is equal to g times g mu nu, the components of the contravariant metric tensor. So substituting that over here, I will get this. But now consider the inner product of g mu nu with the contravariant g mu nu. So that is simply delta mu mu and is equal to 4, as we have already seen. And if I take the derivative of this equation, I will get first delta G mu nu, then G mu nu plus this times derivative of that. that is equal to derivative of this number, which is 0. That means this times this is equal to minus of this times that. And substituting this equation over here, I will have delta of minus square root of minus g equal to, there is this factor of minus coming there, so this is gone, 1 by 2 square root of minus g, then the covariant component g mu nu times delta g mu. But now this g can be written as square root of minus g into square root of minus. And one of those cancels with this. Sorry, not just like this. So g can be written as minus g times minus g. But this minus g can be written as square root of minus g times square root of minus g. Oh, sorry again, this g can be written as minus of minus g. But then this minus g can be written as square root of minus g times square root of minus g. So one of those square root of minus g is cancelled with this one. So we end up with a minus sign, which I write here, and then this square root of minus g, and then this factor. That is. And the second step, we need to compute delta r. Now the Ricci scalar r is given by g mu nu, r mu nu. And if I consider the variation in r because of the variation in delta g, variation in g, then we have delta r equal to, first of all, this quantity r mu nu times variation in g plus g mu nu times variation in r mu nu. And in geodesic coordinates, the Christoffel symbols become 0, and therefore r mu nu, which is defined as r mu alpha nu alpha, can now be written as r alpha mu alpha comma nu minus r alpha mu nu comma alpha plus gamma alpha, the other terms involving gamma terms. But since gamma terms are all 0 in the geodesic coordinates, we can neglect the other two terms. Whereas in these two cases, they involve derivatives of the Christoffel symbols. So in geodesic coordinates, we can set the Christoffel symbols to be 0, but not their derivatives. And therefore, in geodesic coordinates, r mu nu can now be written as r alpha mu alpha comma nu minus r alpha mu nu comma alpha. So now we need to consider delta r mu nu, which is delta of this term, which is this, minus delta of this term, is that. So now we compute what this means. So delta gamma alpha mu alpha comma nu is the variation in gamma alpha mu alpha comma nu as g changes to g plus delta g. So this object is d by dx nu of gamma alpha mu alpha, and therefore this is d by dx nu of gamma alpha mu alpha evaluated at g plus delta g minus d by dx nu gamma alpha mu alpha evaluated at g. But since derivative is linear, I can take this outside, d by dx nu of gamma alpha mu alpha g plus delta g minus gamma alpha mu alpha g. But this difference is the variation in gamma because of the variation in G, and which we write as delta gamma alpha mu alpha. So I can write this as delta gamma alpha mu alpha comma nu. We now show that this object delta gamma alpha mu alpha is a tensor quantity. Remember, gamma alpha mu alpha, the Christoffel symbol is not a tensor quantity, but delta gamma alpha mu alpha is a tensor quantity. To see this, consider the transformation equation for the Christoffel symbols. Gamma bar alpha mu nu, which is Christoffel symbols in the coordinates x bar mu, which is related to the Christoffel symbols gamma in the coordinates x mu in the following way. So gamma bar alpha mu nu equal to dx eta by dx mu, dx c by dx nu, dx bar alpha by dx beta gamma beta eta c minus dx eta by dx mu, dx c by dx nu times d square x alpha by dx eta dx c. Now, delta or the variation of the Christoffel symbol is given by delta gamma bar alpha mu nu equal to this delta of whatever is on the right hand side. Now, this delta corresponds to the variation as a result of the variation in the metric tensor as g goes to g plus delta g. Now, if we look at this expression, the second term on the right hand side does not involve any g, and therefore as g changes to delta g, this factor does not change. So delta of this quantity is equal to 0. And here gamma involves g, and therefore as a result of this variation, the change over here comes from the change over here. So we will have delta gamma bar alpha mu nu equal to this factor times delta gamma beta eta c. So now we see that this is in fact a transformation rule for a tensor of type 1, 2, because this is the corresponding transformation factor. So that means delta gamma is a tensor of type 1, 2. So that's what we have written here. So delta R mu nu is equal to delta gamma alpha mu alpha comma nu minus delta gamma alpha mu nu comma alpha. But this object, as we have seen, is given by delta gamma alpha mu alpha comma nu, and this will similarly be given by delta gamma alpha mu nu comma alpha. Now this object inside is a tensor, as we have just shown, and this is also a tensor because this is variation in the Christoffel symbol as a result of the variation in the metric tensor. So we have this equation delta R mu nu equal to delta gamma alpha mu alpha comma nu minus delta gamma alpha mu nu comma alpha. Remember, we have written this expression in geodesic coordinates, and in geodesic coordinates the Christoffel symbols are 0, and because of that the covariant derivatives reduces to the ordinary derivatives, and therefore we can replace this by say delta gamma alpha mu alpha semicolon nu minus delta gamma alpha mu nu semicolon. Remember, this is exactly equal to this because we are using a geodesic coordinate system, and therefore the covariant derivative reduces to this ordinary derivative. And similarly, this is exactly equal to this in the coordinate system we are using. We are using the geodesic coordinates. Now, this object is a tensor, as we have just seen from this equation. This is also a tensor. The covariant derivative of a tensor is also a tensor. Therefore, this is a tensor and this is a tensor. So and both are of the same type, and therefore the difference is also a tensor. So we have now written in this form. This is a tensor equation valid in any coordinate system. So we have delta r mu nu equal to delta gamma alpha mu alpha comma nu, so not comma, semicolon nu is a covariant derivative minus delta gamma alpha mu nu semicolon. So now we take inner product with g mu nu because that is what we need here. Over here. So when we do that, this is equal to, say, if I multiply it with g mu nu, so I have to do that over here, g mu nu, and here also g mu nu. But now the covariant derivative of g mu nu is 0. Metric tensor is 0, and therefore I can take this quantity inside this brackets. Similarly, this also inside this brackets. So I will get g mu nu delta r mu nu equal to g mu nu delta gamma alpha mu alpha semicolon nu, and similarly in the second term. So in the second term, if I interchange nu and alpha, that is these two, similarly these two, we have g instead of, so I have mu here, instead of nu I have alpha, so g mu alpha, then delta gamma, instead of alpha I have nu, and mu instead of nu I have alpha, and semicolon nu. So now we define a new tensor in the following way. Define it to be g mu nu delta gamma alpha mu alpha. So summation over mu is here, summation over alpha is here, the only free index is nu, and minus this factor. See, this one corresponds to this factor, and then I subtract this from that. So this is g mu alpha delta gamma nu mu alpha, summation over mu and summation over alpha is there, so the free index is nu. So this is a tensor and this is a tensor, so their difference is also a tensor. There is only one free index, so this is a tensor of contravariant rank 1, and I write it as a nu. So looking at this, we can see that this is equal to a nu semicolon nu. So we have g mu nu delta r mu nu equal to a nu semicolon nu. But in one of our earlier classes on a review of tensor calculus, we derived an expression for quantities like this. So this would be given by 1 by square root of minus g d by dx nu times square root of minus g a nu. Then this quantity delta r is equal to this plus this, and we have a delta g mu nu here. This has just been computed. So r mu nu delta g mu nu plus this factor. Now, the variation in the Hilbert action is given by the following. we go back to the, so the first factor is this one, delta square root of minus g times r. The delta square root of minus g is given by this, and delta r is given by this factor, and taking the sum of the two, delta sh can be written in the following way: sum over v, integral over v d4x square root of minus g, then r mu nu minus half g mu nu r times delta g mu nu. So this factor is the one that is appearing here, and this factor is coming from this minus, then the square root of minus g factor is common, and this delta g mu nu is there, and this g mu nu, but then this has to be multiplied with this r. So that is what is appearing here, over here, plus the other factor, which is the second factor over here. So there is the integral will be over d4x, then square root of minus g, then this factor. This factor has a 1 by square root of minus g, and therefore this cancels, and the only term that remains is this. So that's exactly what we have written here. So now this looks like the derivative of a generalized divergence of some quantity in the space-time. So there is a generalized Stokes theorem which will take this to an integral over the surface of this quantity, and that will be proportional to this object, and we see that this object A nu is given by this, and which is proportional to the metric tensor and variation in the Christoffel symbols, which involves the variations in the metric tensor delta g mu nu. And when I take this integral over this using the Stokes theorem, we will get a term that is evaluated on the boundary of this space-time region V, and the integrand will be proportional to A nu, which involves delta g mu nu and the derivatives. Now, as we have already seen, we set delta g mu nu and their derivatives to be 0 at the boundary, and therefore the integral of this term, which needs to be evaluated at the boundary, will turn out to be 0. So we can completely neglect this term, and the resulting variation in the Hilbert action would be given by this. So that is delta sh is equal to integral over the spacetime region V over d4x square root of minus g, then r mu nu minus half g mu nu r times delta g mu nu. So this is only the variation in the first part of the action. We need to consider the matter part of the action now. So the variation will be given by, so since Sm is given by integral over V d4x square root of minus g Lm, its variation is given by, again, integral over V of d4x, then the variation of this object. Now we need to finally arrive at the Einstein's equation, and therefore we choose the variation in this, that is square root of minus g times Lm, to be exactly equal to square root of minus g times k t mu nu times delta g mu nu, so that delta Sm, when I substitute over there, will simply become integral over v d4x square root of minus g k t mu nu delta g mu nu, where this t mu nu is simply the energy momentum tensor that we discussed earlier. So this is a choice that makes the resultant equation the same as the Einstein's equation that we obtained earlier. Now, the total variation in the action is delta sh plus delta sm. So we need to add this to this, and then we will get integral over v d4x square root of minus g. Then these two factors r mu nu minus half g mu nu r plus this factor k t mu nu and this common factor of delta g mu nu outside. So now we need to consider the metric tensor field G mu nu for which this action is an extremum. It will be an extremum provided delta S is equal to 0. Now this delta G mu nu, the variation is taken to be arbitrary, and therefore the right hand side will be equal to 0 provided the quantity within the square bracket is 0. So that will give you r mu nu minus half g mu nu r plus k t mu nu equal to 0. Or in other words, we will end up with this equation, and this is exactly the same equation that we obtained earlier.